Hey everyone, so we're continuing on with chapter 6. Yeah, chapter 6. Gonna run this starting cell. Just gonna run it again so that stupid thing will disappear. And then move my thingy over here. Okay, just checking the audio levels. Yep, okay. So this chapter is based on return values. Very simply, it's what the function gives back to you, right? Every function has a return value. Even if you don't explicitly return something, it'll return none, which is none type, which is a signifier that nothing was returned. So even when you don't return something, you return something that says that you returned nothing, right? So that's like a very simple thing about it. In previous chapters, we've used built-in functions like ABS and round, and functions in the math module like SQRT and POW. When you call one of these functions, it returns a value you can assign to a variable or use as part of an expression. The functions we have written so far are different. Some use print functions to display values and some use turtle functions to draw figures, but they don't return values we assign to variables or use in expressions. In this chapter, we'll see how to write functions that return values. When you call a function like math.sqrt, the result is called a return value. If the function call appears at the end of a cell, Jupyter displays the return value immediately. So yeah, that's a specific to Jupyter thing, which doesn't apply to like a regular IDE. You'd have to print it, but yeah, if it's the last line in a cell in Jupyter, it'll always just print it. Math.sqrt 42 over math.py gives you this weird looking number. If you assign the return value to a variable, it doesn't get displayed, right? So it won't get displayed because it's just assigned to the variable, and that's the last expression that's evaluated, last statement that's evaluated or executed, and that statement evaluates this expression and assigns it to a variable, right? But you can display it later. Or you can use the return value as part of an expression. That is also legal. Here's an example of a function that returns a value. So circle area equals math, blah, blah, blah. And then you use the return keyword to return some value, in this case, area of the circle. Circle area takes radius as parameter and computes the area of the circle with the radius, the last line in a return statement that returns the value of area. If you call the function like this, Jupyter displays the return value, right? Because, I mean, there's a statement there, and that statement is a function call. It's executed, and then a value is returned, and then it's displayed. It's pretty straightforward. We can assign the return value to a variable. There you go. We can a equals circle area, blah, blah, or use it as part of an expression. This is just repeating ourselves. And later on, we can display the value if we assign it to a variable. No problems there. But we can't access area, from within the function, because area is from within the function, so it's not in the scope of the highest level thing, which is known as main, or double underscore main double underscore, right? Name area is not defined because that's him trying to access area from within this function. And some have none. If a function doesn't have a return statement, it returns none, which is a special value like true and false. For example, here's the repeat function from chapter 3. Boom. If you call it like this, it displays the first line of the Monty Python song Finland. Finland, Finland, Finland. The function uses the print function to display a string, but it does not use a return statement to return a value. If we assign the result to a variable, it displays the string anyway. But then if we check the result later, this will be of none type because we don't return any value, right? So result is nothing. Here, because none is null, right? So nothing is shown in the Jupyter display. So you have to actually explicitly use print result, which will print the string none, which is also a reserved keyword, but in this case, it's just printing it as a string. And the return value from repeat is none. Now here's a function similar to repeat, except that it has a return value. So it just takes word and returns it. And we create a line with repeat string. Now if we search for line, it'll give you spam, 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 because the return of the function is actually of none type, right? When you don't return, unless you return something explicitly. Though you could explicitly return none as well. So if you wanted to, you could do that, but you don't have to. Return values in conditionals. If Python did not provide ABS, we could write it like this. If x less than 0, return negative x, else return x. Def absolute value wrong. X. If x less than 0, return negative x. If x greater than 0, return x. I don't understand how this is wrong. Yeah, oh, because it doesn't do anything for 0. If x is negative, the first return statement returns negative x and the function ends immediately. Otherwise, the second return statement is used. However, if your return statement is in a conditional, you have to make sure that every possible path through the program hits the return statement. For example, there's an incorrect version of absolute value, this, and if you give it 0, it just crashes out. Oh, sorry. That's because there's a name error because I didn't run that cell. Now let me run the cell. Oh yeah, then it returns none because that's a silent failure. So it won't actually give you a syntax error like it might in some languages. But here basically, because not all paths can be explored, there's an implicit return none, right? If a function executes and there's no explicit return statement that it hits, then it will return none. And because 0 doesn't go accept any of these conditionals, it just goes through all of the function code and never hits a return statement that was explicitly stated, so it returns none. That's why this, now if you print this and then do that, boom, none. So anyways, moving on. We got nothing. Here's the problem. When x is 0, neither condition is true, and the function ends without hitting a return statement, which means that the return value is none, so Jupyter displays nothing. And as another example, here's a version of absolute value with an extra return statement at the end. If x is negative, the first return statement runs and the function ends. Otherwise, the second return statement runs and the function ends. Either way, we never get to the third return statement, so it can never run. Code that can never run is called dead code. In general, dead code doesn't do any harm, but it often indicates a misunderstanding and might be confusing to someone trying to understand the program. Yeah, absolutely, 100%. Incremental development. As you write larger functions, you might find yourself spending more time debugging to deal with increasingly complex programs. You might want to try incremental development, which is a way of adding and testing only a small amount of code at a time. As an example, suppose you want to find the distance between 2 points represented by the coordinates x1, y1, x2, y2. x2, y2 by the Pythagorean theorem. The distance is x2 minus x1 squared plus y2 minus y1 squared, and take the square root of the whole thing. First step is to consider what a distance function should look like in Python. That is, what are the inputs, parameters, and what is the output return value? For this function, the inputs are the coordinates of the points. The return value is the distance. Immediately, you can write an outline of the function. Def distance x1, y1, x2, y2. The version doesn't compute distances yet. It always returns 0, but it is a complete function with a return value, which means that you can test it before you can make it more complicated. To test a new function, we call it with sample arguments. Boom, boom, it's just going to return 0 because that's all that's defined. And then we actually do the math in here. I choose these values so that the horizontal distance 3 and the vertical distance 4, that way the result is 5, the hypotenuse of 3, 4, 5 triangle. When testing a function, it is useful to know the right answer. At this point, we have confirmed that the function runs and returns value, and we can start adding code to the body. A good next step is to find the differences x2 minus x1 and y2 minus y1. Here's a version that stores the value in temporary variables and displays them. Okay, if the function is working, it should display dx is 3, dy is 4. If so, we know that the function is getting the right arguments and performing the first computation correctly. If not, there are only a few lines to check. Boom, boom, boom. It still returns 0. Good, so far. Next we compute the sum of squares of dx and dy. and d squared is d squared. And then again, we can run the function, check the output, which should be 25. And then we can just return that. Or finally, we can use math square to compute the distance, check the distance, and then you can actually return that result. Right? Honestly, you could skip this and you could do this like this as well. Return, right? It's not a huge difference, and it makes the code a bit more readable to keep it separate. But I tend to do the other thing, which is not necessarily nice, but whatever. This version of distance is a pure function. If we call it like this, only the result is displayed. And if we assign it to the result of the variable, nothing is displayed, because the print statements we wrote are useful for debugging, but once the function is working, we can remove them. Code like that is called scaffolding because it is helpful for building the program, but is not part of the final product. This example demonstrates incremental development. The key aspects of this process are starting with a working program, make small changes, and test after every change. Use variables to hold intermediate values so you can display and check them. Once the program is working, remove the scaffolding. At any point, if there is an error, you should have a good idea of where it is. Incremental development can save you a lot of debugging time. So yeah, that's true. Essentially just, have some scaffolding, some logs or some print statements, whatever you need to help you build out your function and remove it once it's done. And like just doing that in tiny small steps. And with the power of functions, you can break things down. So if you wanted, you could create another function that calculates x2 minus x1 or y2 minus y1, right? Just some subtract function, right? And or a function that returns both of these. You just give it all and it just gets all of these for you, and move this out somewhere else, right? And call that function get distances, right? Something like that. Anyways, Boolean functions. Function can return Boolean values true and false, which is often convenient for encapsulating a complex test in a function. For example, is divisible checks whether x is divisible by y with no remainder. If x modulo y equals 0, return 2, else return false. Here's how we use it. Is divisible 6, 4, divisible. I'm just gonna boom, 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 show that to you guys. It's false for 4 and it's true for 3, which yeah, makes perfect sense. Inside the function, the result of the double equals operator is a Boolean, so we can write function more concisely by returning it directly. So instead of doing this and return true, false, we know that this expression, once evaluated, will return true or false, right? So you can just do return this expression and it will be true or false, and you get the answer right away. Boolean functions are often used in conditional statements. So if is divisible 6, 2, print divisible. It might be tempting to write something like this, but the comparison is unnecessary. Why? Because when you run is divisible, it already returns a Boolean. So if true, do this. If false, do this, right? So you don't need the equals true check. It's just redundant. Recursion with return values. Now that we can write functions with return values, we can write recursive functions with return values. And with that capability, we have passed an important threshold. The subset of Python we have is now Turing complete, which means that we can perform any computation that can be described by an algorithm. To demonstrate recursion with return values, we'll evaluate a few recursively defined mathematical functions. A recursive definition is similar to a circular definition in the sense that the definition refers to the thing being defined. A truly circular definition is not very useful. Vorpal, an adjective used to describe something that is vorpal. Yeah, that's truly circular, and that's just useless. If you saw that definition in the dictionary, you might be annoyed. On the other hand, I am annoyed. If you looked up the definition of the factorial function denoted with the simple exclamation point, you might get something like 0 factorial equals 1, n factorial equals n times n minus 1 factorial. This definition says that the factorial of 0 is 1, and the factorial of any other value n is multiplied by the factorial n minus 1. If you can write a recursive definition of something, you can write a Python program to evaluate it. Following an incremental development process, we'll start with a function that takes n as a parameter and always returns 0, right? So we can start with that. And then we modify it. If n equals 0, return 1, else return 0. Okay, getting closer. Else recurse equals factorial n minus 1, return n times recurse. And we just keep doing that. And here's just another showcase of how that will play out. It'll first go all the way down to the lowest, and then it'll pop back up to the top. And here's, they're going to show us a nice little diagram describing that. Yeah, see, it goes from top to the bottom, and then it goes from bottom back up to the top. And we are shown being passed up the stack. In each frame, the return value is of the product of n and recurse. In the last frame, the local variable recurse does not exist because the branch that creates it does not run. Yeah, because you hit the base case and the base case just returns, right? You don't need the variable recurse or the local recurse. Following the flow of execution is one way to read programs, but it can quickly become overwhelming. An alternative is what I call the leap of faith. When you come to a function call, instead of following the flow of execution, you assume that the function works correctly and returns the right result. In fact, you are already practicing this leap of faith when you use built-in functions. When you call ABS or math.sqrt, you don't examine the bodies of those functions, you just assume that they work. The same is true when you call one of your own functions. For example, earlier we wrote a function called isDivisible that determines whether one number is divisible by another. Once we convince ourselves that this function is correct, we can use it without looking at the body again. The same is true of recursive programs. When you get to the recursive call, instead of following the flow of execution, you should assume that the recursive call works, and then ask yourselves, assuming that I can compute the factorial of n minus 1, can I compute the factorial of n? And the recursive definition of factorial implies that you can by multiplying by n. Of course, it's a bit strange to assume that the function works correctly when you haven't finished writing it, but that's why it's called a leap of faith. Yeah, so that is very weird series of paragraphs, but I get what it's saying. Like, sometimes you do need to assume correctness and continue, and then come back to test it later. Yeah, that is kind of true, but also I wouldn't necessarily recommend it, but whatever. After factorial, the most common example of a recursive function is Fibonacci, which has the following definition. Fibonacci of 0 is 0, Fibonacci of 1 is 1, Fibonacci of n is Fibonacci of n minus 1 plus n minus 2. And translated into Python looks like this. Yeah, if n is 0 or n is 1, return 1 or 0, else return Fibonacci n minus 1 plus n minus 2. If you try to follow the flow of execution here, even for small values of n, your head explodes. But according to the leap of faith, if you assume that the two recursive calls work correctly, you can be confident that the last return statement is correct. As an aside, this way of computing Fibonacci numbers is very inefficient. In Chapter 10, I'll explain why and suggest a way to improve it. I hope he does, because yes, it is very inefficient. But I also actually don't know what the efficient way to do it is. I'm sure there's some mathematical trickery you can use. What happens if you call factorial and give it 1.5 as an argument? Yeah, it'll never hit a base case, basically. You'll just hit a recursion error because n equals 0 or n equals 1 just doesn't work. Fibonacci is integers only. It looks like an infinite recursion. How can that be? The function has base cases where n equals 1 or n equals 0. But if n is not an integer, we can miss the base case and recurse forever. There you go. In this example, the initial value of n is 1.5. In the first recursive call, the value of n is 0.5. In the next, it is negative 0.5. From there, it gets smaller, more negative, but it will never be 0. To avoid infinite recursion, we can use the built-in function isInstance to check the type of the argument. Here's how we check whether a value is an integer. Is_instance 3 int, which is true, or is_instance 1.5 int. So if not is_instance n comma int, print factorial is only defined for integers, return none. You actually don't even Yeah, actually, no, you do. You do. Um, you could actually just put everything within an initial if block of if is instance true or something like that. Anyways, I don't want to think about how to refactor this efficiently, but this is true, right? You want to check for that. You want to be very careful with recursion if you're not hitting a base case, you know? Um, and if I give it something like that, factorial is only defined for integers, factorial is not defined for negative numbers. Um, and honestly, I think, oh, you want separate messages, never mind. Debugging. Breaking a large problem into smaller functions creates natural checkpoints for debunking. If a function is not working, there are three possibilities to consider. There's something wrong with the arguments the function is getting, that is, a precondition is violated. There's something wrong with the function, that is, a postcondition is violated. Caller is doing something wrong with the return value. To rule out the first possibility, you can add a print statement at the beginning of the function that displays the values of the parameters and maybe their types, or you can write code that checks the preconditions explicitly. If the parameters look good, you can add a print statement before each return statement and display the return value. If possible, call the function with arguments that make it easy to check the result. If the function seems to be working, look at the function call to make sure, make sure the return value is being used correctly or used at all. Adding print statements at the beginning and end of a function can help make the flow of execution more visible. For example, here's a version of factorial with print statements. Yeah. So there's just more notes on debugging and how to do it appropriately. Add more print statements. Factorial 13. If you're confused about the flow of execution, this kind of output can be helpful. It takes some time to develop effective scaffolding, but a little bit of scaffolding can save a lot of debugging. True. Glossary of terms. So yeah, Turing complete. This is a formal definition that I did not actually know before this, but it's really nice. That because all of programming can be encapsulated by very few small concepts, and then from that you can do basically everything, right? And everything else is just language-related features. So the exercises. Ask a virtual assistant. In this chapter, we saw an incorrect function that can end up without returning value and a version that has code that saw the following example, which is correct but not idiomatic. Ask a version what's wrong with each of these functions if it can spot the errors and improve the style. Then ask write a function that takes coordinates of 2 points and see if the result resembles the version of distance we wrote in this chapter. Sure, you could do that. It's kind of nice. Use incrementable development to write a function called hypot that returns the length of the hypotenuse of a right triangle given the lengths of the other two legs as arguments. Note that there's a function in the math module called hypot that does the same thing, but you should not use it for this exercise. Even if you can write the function correctly, on the first try, start with the function that always returns 0 and practice. Okay, yeah. So I'm not gonna get into that, but basically yes. Write a Boolean function is between, which returns true if x is less than y, and y is less than z, or if z is less than y, and y is less than x, or false otherwise. Basically, if y is between x and z, return true, else false. And yeah, Ackermann function, am-1 comma amn-1, write a function where that evaluates the Ackermann function. What happens if you call Ackermann 5. Yeah, I don't know how this is to be done, but some sort of recursive function. Good practice. I'm not going to do it, but good practice. This is going to be like a recurring thing. I'm not going to do it, but good practice. A number a is a power of b if it is divisible by b, and a over b is a power of b. Write a function called isPower that takes parameters a and b, returns true if a is a power of b. Note, you will have to think about the base case. Exercise, greatest common divisor, so that's another function. Yeah, so functions at the wazoo. That's chapter 6. Good set of exercises here. These exercises are genuinely very interesting and very good. Practice, especially if you really try to do them, and you're just starting off, these are genuinely very good. So yeah, I think that's it for this video. We're gonna call it. Thank you all so much. Have a great one. Bye bye.